Hi, my name is Jordan Inacio, and I'm a mechanical engineering graduate student at Lehigh University. And today, I'll be presenting on a collaborative project between my lab and the Biederman Lab for Orthopedic Research at the University of Pennsylvania titled Patient-Specific Alignment Fixture Improves Agreement Between Physical and Virtual Biomechanical Tests. As we know, benchtop cadaveric biomechanical testing is the gold standard for evaluating both the mechanical properties of bone and the performance of orthopedic implants. And during a benchtop biomechanical test, it is important to ensure that the mechanical axis or the anatomic axis of the bone being tested is in line with the mechanical axis of the testing machine in order to replicate the loading conditions in vivo. And in theory, identifying either axis is simple, yet in practice, this can be very challenging to accomplish. And the effect that this malalignment has on the test measurements is still unclear. And therefore, the objective of our study was to design an adaptive specimen-specific potting fixture that controls physical specimen alignment prior to potting. This fixture would also ensure replicable alignment between physical and virtual tests. It was hypothesized that the specimen malalignment would be associated with significant differences in the apparent axial stiffness and torsional rigidity. 3 matched pairs of fresh frozen cadaveric specimens were utilized in this study, a total of 6 forearms. Each forearm underwent a clinical CT scan with the same scanning protocol. A bone density calibration phantom was included in each scan to later convert from radio density to bone mineral density. This image stack was imported into the materialized suite in which the virtual model of each radius was recreated. A tetrahedral mesh size of 0.75 millimeters was applied to the surface and to the volume. Patient-specific material properties were then applied to each model. This model was imported into ANSYS, and then boundary conditions were applied. After the virtual models were created and properly aligned, a custom 3D printed alignment fixture for potting purposes was created, which has patient-specific 3D printed inserts that ensure that the alignment of the physical specimens match that of the corresponding virtual models. Once all 6 specimens were potted, they were then mechanically tested to calculate the axial stiffness and the torsional rigidity. Each radius model was mechanically tested in the aligned configuration, as well as in 4 additional translational malaligned configurations. To obtain these configurations, an offset of 10 millimeters was placed either in the posterior, medial, anterior, or lateral directions. The results from these tests are shown in the radar plots on the right. What's being plotted here is the alignment percent error from the aligned configuration, and each radius was assigned its own color and line. The same tests were run, but for the angular malaligned configuration, in which a 5-degree malalignment was applied in the anterior-posterior view and in the medial-lateral view. And on the right-hand side, you can see the results from both of those tests. On the top, again, is the simulated axial stiffness and the percent error from the aligned configuration. And on the bottom is the virtual torsional rigidity, and that is the percent error from the aligned configuration. From these results, we concluded that a small specimen translational or angular malalignments greater than 10 millimeters or 5 degrees from the test axis, respectively, cause significant errors in measured axial stiffness of the virtual bone models, with errors as high as 65%, whereas torsional rigidity values were not sensitive to errors caused by malalignment, with errors less than 4% in all directions. This suggests that torsion tests should be used as a summary mechanical measure whenever possible. That concludes my lightning talk, and I'd like to thank my advisor, Hannah Daly, and our collaborators, Michael Hast and Danielle Cristino.